Hello! Today we are going to present the final project for Transport Processes 1. In here, we apply the knowledge acquired during the semester. The first problem shows a heat exchanger which handles 0.0567 cubic meters per second of water through the pipe system. We can see the system in the figure shown. The total pressure drop between the valves, including the valves, is 110 kilopascals. Both valves are gate valves open 3/4. We want to know what size pipe is required for this system, aka the diameter value. We consider the system to be stainless steel. Following, my classmate Manny is going to explain the process we used to solve this problem.
First of all, we have to make the global energy balance to discard the irrelevant values. Since we are only designing the heat exchanger, we can assume that there is no heat. The system also has no work, no potential energy, no kinetic energy, and no velocities as well. We also assumed that the massive flow rate tends to 0. Now, the information given by the problem state are delta P, the volumetric flow rate. We assume the density. We know our length and value of K. We read them from the tables. Therefore, the unknowns are velocity, diameter, and area. The diameter is included in the head loss term, but cannot be solved for directly, as the friction factor also depends on diameter. Inserting numerical values, we are going to assume that our friction factor value is 0.0042, parting from the value given by the professor in class. Now, by isolating D in our formula, we obtain the value of D to be 0.102 meters. With this value, we can now calculate the area and the velocity in order to calculate the Reynolds number. Once we have the Reynolds number, we go to the graphs to check the assumed value of friction factor. We notice that this value is the same that we assumed. Therefore, the size pipe required for this problem is 0.102 meters, and that will be the final answer.
Water at 20 degrees Celsius is to be pumped through the system shown below. The operating data for this motor-driven pump are as the following table shows. The inlet pipe to the pump is 0.06 meters in diameter commercial steel and 8.5 meters in length. The discharge line consists of 60 meters of 0.06 meters in diameter steel pipe. All valves are fully open globe valves. Determine the flow rate through the system.
First, we perform the energy balance. As we can see, the balance equation results in power is equal to height difference plus head losses. Then we plot the head and efficiency curves. Assuming the highest efficiency of the pump, we give the flow rate a value of 0.004 cubic meters per second. Next, we calculate the area with the given diameter in order to calculate the velocity. Once we have the velocity, we calculate the Reynolds number. As we can see, we have a turbulent flow. Since it's a turbulent flow, we use the following equation to find the friction factor. We get a friction factor of 0.0088. In this problem, we consider 4 standard 90 degrees elbows and 4 fully open globe valves. Following, we calculate the head loss considering the values of K for the losses of valves and elbows. Once we know our total head loss, we calculate the head using the height difference. As a result, we get a head of 61.4 meters. Finally, we calculate the work needed in horsepower. Hence, assuming the highest efficiency of the pump, the flow rate for the system is 0.004 cubic meters per second.